Yes, hope all of you are doing great. So today we are going to look at a concept in logarithm and indices, and that is the concept of integral exponents. So we're going to see that we can be able to, of course, achieve different types of exponents. For instance, apart from the integral exponents, we're going to also to look at what we refer to as rational exponents. But in this case, of course, we had already looked at a specific notation that was being used for exponents, which we referred to as exponential notation, and which we gave as just an arbitrary number n given as a b. And then we said from this particular representation for an exponential notation, this n represents a number which basically is going to be the product of this section that we refer to as power, and then this one is going to be referred to as the base. Now this one builds for us a foundation for describing this integral exponents, in that of course these different parts of an exponential notation is going to give us a clue on how we can be able to represent these specific integrals. Now in this case, I can just use our illustration that is on the board still, whereby we are going to see that when the exponent b is a positive integer, then it denotes the number of factors whereby these factors are going to be multiplied up to a point whereby they are going to result in this specific whole number. Therefore, I can be able to illustrate our exponential notation as a multiplied to b factors, which basically we have said that is if a is a positive integer, then we're going to see that this is going to be n is going to be achieved from a number of multiplication of this specific base up to b factors in order for us to attain n. Therefore, we're going to see that this one is applicable for positive integers, as I've mentioned. But we're going to see that whenever we are trying to represent integral exponents with multiplicative inverse, I'm going to, we'll just use this space. Now in this case, we have talked about this particular factor way of representation of these specific exponential notations using positive integers. Therefore, this is the implication of in that particular case. But if we had a case whereby the number n is a product of a and b is a negative integer, then we're going to use a different representation for that, which basically I'm going to just do away with this part so that we can be able to use it to explain that. So if n is a result of the base a, which has been multiplied using the negative integer b, then therefore, as we have said, this is going to be a multiplicative inverse, whereby we're going to have all the products being a factor of a, which is an inverse, up to b factors. Therefore, this applies to negative integral exponents. And therefore, from these two particular representations, we can be able to have what we call integral exponents, which have been represented for positive and negative integral exponents respectively. Now for zero exponents, we're going to have a third condition. So this is the second one for negative. The first one was if we have a zero exponent. Now for a zero exponent, in this case, I refer to a situation whereby we're going to have a number being a product of a base which has been raised to 0. Therefore, this is going to represent unity, whereby this a can be an arbitrary number. For instance, if I write 2 raised to 0, then this is going to be unity, which is 1. So therefore, these are some of the ways in which we are going to use in recognizing the integral exponents, which you are going to find largely in mathematics and some of the sciences. So catch us in our next video where we're going to look at rational exponents, and of course which we are going to use in order to find the relationship between this and what we have already discussed, and how they can be able to be related to the rational exponents. So that is it for today, guys. Bye. God bless you.